Hello and good morning, everyone. My name is Arshad, and I'm docent and the lead researcher in Institute of Aeronautics, Riga Technical University. Today, I will present my research work. The topic is design optimization of low-speed aerofoils for the UAV applications. These are the contents of my presentation, and I will explain them one by one. So let's start with the introduction. Aircraft wings and airfoil designs are always interesting from the beginning. Designing also changes always with the new applications. If we talk about these days, then during these days, low-speed aerofoils are getting more attention. That is primarily due to the introduction of new designs in unmanned aerial vehicles, wind turbines, and some light aircraft. So when we talk about low Reynolds number or low-speed aerofoils, it means that the Reynolds number should be less than the 1 million. About low-speed aerofoils, the designs of high-speed aerofoils are well developed. But when we talk about the low-speed aerofoil, there are some problems related to the viscosity of the flow and the laminar flow separation, which is generated always at the surface of the aerofoil, and because of that, the performance and sustainability of the aerofoil is always affected. Therefore, the understanding of this transition flow is very much important for the design aspects. Two-dimensional design aspect is better to understand. That's why I will mainly discuss only the two-dimensional design for the aerofoil. Now for the design of the aerofoil, the classical potential flow theory is still valid and it's still applicable. And X-foil is a very famous and very convenient tool, and probably the best tool which is widely used for the evaluation of the aerodynamic characteristics and the performance of the aerofoils. Not only aerofoils, but also wings, aircraft, even the blades of the turbines and compressors as well. However, there is a limitation in the X-foil, and that limitation is that it's mainly is suitable for the non-viscous effects. And when viscosity comes, it's not really convenient. And when we talk about the viscosity, here comes the importance of CFD, the computational fluid dynamics, which I will discuss in detail here, and which was performed for this work as well. Okay, by keeping this in our mind, I set 4 clear objectives for my research. First is to develop a fast and reliable method for designing and optimizing the new aerofoils. Once the new aerofoil is designed, second stage is to using an accurate method for the aerodynamic characteristics of this new aerofoils for the improvement of these characteristics. A multidisciplinary software or optimization tool we designed for our work, and I will present here soon. And finally, once we have designed this tool and we have designed new optimized software, new optimized aerofoil, we can create an optimized workflow to generate new aerofoils. So it's not limited, but it can be, the range will be very wide for different designs of the aerofoils. For this approach, so for this, the methodology was divided into 4 parts. At first, the selection of the low-speed aerofoils was made. In the second step, X-foil analysis was performed, and the results were compared with the actual data. In the third step, an algorithm and code was developed for the improvement of the selected aerofoil, and finally, the CFD computational analysis was performed. Before I move to the results, I would like to explain the methodology we developed. So it's a short view of the code we developed for the optimization process. X-foil is common, but it's very slow and it always requires user interface. On the other hand, Mode Frontier is relatively new and it's lesser used module for the optimization. So we developed a code and integrated these two software together in the Mode Frontier environment. By doing this, we increased the optimization performance, made it automatic with no user interface at all. So that is the main advantage of this methodology we developed. And finally, we improved the speed of the optimization process. Now, X-foil analysis. We carefully choose 2 existing low-speed aerofoils. These aerofoils are used in UAV applications right now, these days. At first, the comparison of the compared results, like we computed the results of X-foil, and we compared these results with the actual data, which is taken from the wind tunnels. And the comparison showed a very good agreement. And now I will show you the results. So you can see the results on screen. These are the results of the 2 selected aerofoils which we selected for the UAVs. These results present the comparison of the computed aerofoil results with the actual data. Main aerodynamic parameters were computed, such as the coefficient of lift, coefficient of moment, and the ratio of lift and the drag. Only small deviations are there, which are very commonly found in the computational results. However, if you see these results, confirm that X-foil is a reliable tool for the designing of the aerofoils. Further on as we developed the new method to design the aerofoils, so this is the new aerofoil what we designed. So the next step was to improvement of the characteristics of the existing aerofoil and generate a new aerofoil from the existing one. How we did this? We used our newly developed method and optimized the aerofoil. You can see here the existing aerofoil in red color, which was the base aerofoil, the mother aerofoil I would call it, right? And the new aerofoil, which is optimized, is in the blue color, and I would call it the modified. So the aerofoil is SG6043, and we named it SG6043 mod from the modification. Okay, we found that by using our method, the optimization parameter was improved to 10%, which is actually a pretty good improvement in the overall designing process. The next step was to study the results and compare these results. So the results of the newly designed aerofoils in terms of aerodynamic characteristics I just present here. First, as you can observe that the newly optimized aerofoil produces more lift than the original base aerofoil. As you can see the red color curve, it produces higher lifts than the original aerofoil. Similarly, you go to the drag. The drag is reduced in the new aerofoil, but away from the design point, there's slightly higher drag, which is due to the laminar separation bubble, which I explained in the beginning of this presentation. This separation of the flow mixes with the turbulent interaction of the flow just above the surface of the aerofoil, which I will show you soon in the CFD analysis. Also, if you see the higher values of moment coefficients in the new aerofoil were observed, which was optimized. This is due to the increased camber of the optimized aerofoil. The new aerofoil design, we increased the camber, so in this way the aerofoil can sustain higher loads, especially aerodynamic loading at the nose down positions. Okay, the CFD analysis, this is the second level of verification of our results. For the understanding of the flow mechanism and the viscosity effects in the aerofoil, which were absent in the X-foil, we did a further tier of analysis. So a computational fluid dynamics analysis was performed. We created the mesh in the ANSYS ICM, and we used ANSYS CFM and ANSYS Fluent for the simulations. I will not go into the very much details, but mesh independence study was also performed, so the results are independent of the number of elements we used for the meshing. Okay, now same results what we had from the airfoil, now they are compared with the CFD results. So the CFD results of new aerofoil were compared with the airfoil results what we obtained previously. As we can observe that the lift coefficient is in very good agreement in both the cases. So CFD results and the airfoil results are in good agreement, and don't forget that these results were the same experimentally as well. So actual data was matched by the airfoil data, and this our data is also matched by the CFD analysis as well. Lift coefficient is in good agreement, so we can say the fluent predicts an earlier stall compared to the airfoil due to the transition flow separation on the aerofoil surface. So there is an early stall in the CFD analysis. This is actually due to the separation bubble, which I will show you soon. Due to the same flow reasons, separation bubble, slightly higher drag values are obtained in the CFD analysis. This is due to the laminar separation bubble. However, the overall predicted values of the CFD are very much in good agreement with the airfoil, which we did while designing the aerofoil. So here, in this slide, the flow mechanism over the aerofoil is presented. The formation of laminar separation bubble is observed exactly at the upper surface and as well as the lower surface of the aerofoil. These surfaces of the aerofoil produce this bubble, and this bubble is in fact the reason of the increased drag, what we saw in our computational results. Also, these two bubbles have reversed flow inside, which creates a dead zone over the aerofoil surface. The bubble also increases in size, and the local thickness of the aerofoil also increases the drag, and that exactly was observed in our results. It was also observed that the laminar separation bubble has a relationship with the angle of attack. At the zero angle of attack, there are two laminar separation bubbles, and both on the top and the bottom of the surface, as you can see in the velocity contours. As the angle of attack increases, the lower surface laminar separation bubble disappears, and only one bubble is observed at the top surface. This is possible due to the adverse pressure difference and pressure distribution along the surface, but how exactly the boundary layer reacts on this flow and in laminar separation bubble, this is a very complicated topic, and it should be discussed separately, and our group has already started to work on this for the future concerns. Finally, we did analysis on 4 different angle of attacks, and these angles were studied, and it was further found that with the increase in the angle of attack, the laminar separation bubble decreases. So higher the angle of attack, lower the separation. The complete study was further applied to different aerofoils for the further confirmation. So all the process was repeated with another aerofoil type. Results were pretty much positive, and the results were similar to the previous case. So I will not go into the details because it's only the repetition of the previous case. So I will quickly move to the conclusions now. So from this research work, we can conclude the following points. The proposed method of optimization and in improving the aerofoil characteristics is highly efficient, number 1. Number 2, the methodology we developed for the improvement of the design of the aerofoil, this improves the process by reducing the processing time and the user interface, because it's completely automatic process. So there is very lower chance of the errors which are usually concerned with the user interface. Also, CFD results validate the optimization method which was developed for this study. So we had 2 levels of validations, and both the methods confirm that our designing software methodology is validated. Most importantly, this method, what we developed, is applicable for the designing of large range of low-speed aerofoils. So it's not related to only one type of design. Hundreds of designs within the low-speed range can be designed by using our methodology. Future work, we will develop a UAV wing based on the work we did here, and also there will be a final and third level of comparison and validation of results. We will make wind tunnel experiments in the future. Also, we will study the mechanism of the laminar separation bubble, and in detail we will study the boundary layer theory to avoid this separation. In this way, the performance of the UAVs can be improved. My idea is that we can use vortex generators. We also started working on that, and we'll continue in the future. This work was supported by the European Regional Development Fund, and this is the funding I received for my postdoc project, and I'm really grateful to that. I'm grateful to my university, and also thank you very much the conference organizers for giving me a chance to present my work. That's it, and thank you very much.